seminar of the year 2022 Applied Math Seminar. Today we have the pleasure of having for opening speaker Alex Bihlo. He's an associate professor at the Department of Mathematics and Statistics and cross-appointed with the Department of Computer Science at Memorial University of Newfoundland. He got his PhD in 2010 from the University of Vienna. Then he had several postdoc appointments, including at the CRM, McGill, and Memorial. He won a Payne's Early Career Award in 2018, and is currently Canada Research Chair in Numerical Analysis and Scientific Computing. So it's a great honor for us to have Alex speaking today. He will be talking about recent advances at the intersection of deep neural networks and scientific computing. So take it away.
Thanks so much, Simone. Thanks for having me. As I guess Simone mentioned, I guess when I came to Canada in 2011, so Montreal was my first stop. So I was 2 years at the CRM, and I still sort of fondly, I guess, remember having lived in the McGill ghetto and like walking every day over Mont-Royal to the CRM at the University of Montreal, and then of course also a great time at McGill. So it's a pleasure to be here. It would be nice to be here in person, but I guess pandemic is still having different plans for us. But it's still great being able to give this talk here on some quite recent work. I mean, as recent as basically it's still ongoing, with my colleague and former supervisor, Roman Popovych at the University of Vienna, just talking about how we can use neural networks to solve, in fact, differential equations on surfaces. We started out with basically doing this on the sphere for weather prediction, essentially, and then kind of realized that this method is really nice because it's fully meshless, and because it's fully meshless, it's relatively easy to solve equations on arbitrary manifolds. It's a very sort of streamlined outline here. I introduce what is called physics-informed neural networks. I mean, maybe by now most of you know already what that is, but it's still, I mean, like in terms of popularity, relatively recent. I think it was came to the on the radar in like 2018, 2019. I mean, it's an older method really, and I'll talk about this. But really, I guess it only took off the last few years or so. So I'm going to talk a little bit about this, and then give some examples on solving differential equations on manifolds. But before we do this, okay, why do I care about this, or why should we care about this? Well, because like technically a lot of real-world applications require us to solve differential equations on complicated surfaces. And like the chief of them for me, and that's always sort of near and dear to me, is numerical weather prediction. So if you want to do sort of non-academic numerical weather prediction, you have to do this on the sphere. But there is also other applications out there, of course, like if you want to study how patterns form on animal coats, when in computer vision, computer graphics, you want to generate textures on arbitrary surfaces. So then you have to be able to solve differential equations on manifolds. Unfortunately, I mean, that's true, of course, for almost all differential equations. They rarely have analytical solutions. And in particular for solving differential equations, say like an animal coating and so on. So there is rarely anything analytically available. So we have to resort to numerical analysis, of course. Of course, I mean, so if it comes to numerical analysis, if you take a course in numerical analysis, chances are high that you spend like 80%, 90% on solving differential equations in Cartesian coordinates. And that sort of has been, of course, extensively done over the last several decades, or even now a century or so. But yeah, when it comes to solving differential equations on surfaces, that is sort of less frequently done in the literature. And I guess like one reason, obviously, is then you don't only have to treat the differential equation, deal with solving the differential equation. You also have to somehow represent the surface. So that becomes like a whole separate topic and issue. How do you actually mesh your surface? And here I don't talk so much about the meshing, like the examples that I show you, which is basically take a mesh from a repository, and I just focus on the discretization part here. So how is that done in the literature? Well, the most straightforward idea, of course, is to use what's called intrinsic coordinates. So we essentially simply express our differential equation in a coordinate system that conforms with our surface. Like one like particular example, of course, is weather prediction. Like on the sphere, we use latitude, longitude coordinates, and then basically express our differential equation in latitude, longitude coordinates. And once we have this, it's an orthogonal coordinate system. So we can use, again, traditional numerical methods for this task. So this is conceptually simple, and it's nice because, like I said, you don't have to invent a new method, really, right? You can use finite differences, finite elements, finite volume methods, but the sort of complication arises because hardly ever are these intrinsic coordinates free of singularities. And once again, I guess, like if you formulate this in the language of differential geometry, say, of course, the most classical example that you see in a course on differential geometry is the sphere. And we know that it's not possible to cover the sphere, in fact, with a coordinate system that uses a single coordinate chart. So, and then basically you have to use multiple charts. There is an overlap, in fact, and you have to deal with this. So in sort of more, I guess, direct terms for latitude, longitude coordinates, there is a singularity at the poles. And that becomes a problem, of course, for weather prediction, because you can't define a wind field properly at the poles anymore. And I mean, that problem has been studied, of course, like for 60, 70 years now in numerical weather prediction. So there is a long history actually of proposing new ways of solving the equations of fluid mechanics on the sphere. So there is a great, I mean, now already 10-year-old review paper by a colleague who actually works at Environment Canada, worked at, I don't know if he still works there, but he should be in Dorval. So there has been some work done, in fact, on this problem in Montreal. So lots of different ways how you can mesh the sphere, but a lot of the sort of problems that arise is that no matter what mesh you choose, you typically get some sort of artifacts, like some sort of grid imprinting, in fact. So it's still a staining problem. What's the best coordinate system to use on the sphere? So that's, in fact, your first approach. So two approaches. The first one is the intrinsic coordinate approach. Second approach is an extrinsic approach, where you use so-called embedding methods. You simply embed your given surface in a higher dimensional space and then simply solve your differential equation in this extrinsic coordinate system. And then you only have to worry about restricting this to the surface itself. There's two methods. I mean, there is lots and lots of methods out there, but two methods that appear all the time, I guess, in this field is first is the closest point method, proposed by our colleagues at SFU. And then there is another sort of slightly newer approach based on radial basis functions. And the advantage of this approach is that then you essentially just deal with Cartesian coordinates. So there is no coordinate singularity anymore. You deal with Cartesian coordinates and still have to just worry about projecting, in fact, your differential operators, in fact, to the surface of your manifold. And that's the approach we use here. In particular, basically an adaptation of this method by Shankar here, who has done this for radial basis functions. We use, in fact, this approach for neural networks. So that's, in fact, a long-winded motivation. So yeah, we want to solve differential equations on manifolds. How do we do this? Well, let's use extrinsic Cartesian coordinates with an embedding method. And the embedding method of choice that we want to try out here is based on neural networks. So let's talk about neural networks then, and in particular neural networks for differential equations. Well, of course, I mean, I guess this is an applied math seminar. You know how to solve differential equations numerically. So I guess finite difference, finite elements, finite volumes. But recently, and it's really taking off, I guess. So it seems that there is, like every day, there is papers appearing where people use neural networks for solving differential equations in different fields of the mathematical sciences. And I mean, it goes by the name of physics-informed neural networks. But really, you can trace this actually back to like an older reference here. I mean, maybe there is even older references. That is one that is also quite well cited by Lagares et al. Sort of around 15 years old now, where sort of at least core ideas of this method have been proposed. And then there's like everything else related to deep learning. I mean, up until maybe 10 years or so ago, research on neural networks was still very much a fringe topic, because simply the computer hardware wasn't there yet, right? And only with, I guess, the advent of sort of more capable GPU computing abilities, and also, I guess, the ease of use of frameworks such as TensorFlow and PyTorch has made neural networks really, I guess, mainstream in I guess, scientific computing. So this method, like an adaptation, extension of this method by Lagares, is nowadays used as nowadays referred to as physics-informed neural networks. And the idea is relatively straightforward. I mean, in computer science or like data science, we typically train neural networks based on data, right? So like we take a pile of data, train, in fact, our neural networks in a supervised fashion, and solve a given sort of data science problem. But for scientific computing, we not only have data, we also have basically a process that gives rise to the data that we have. And this process in general is a differential equation. So in PINs, we try, in fact, to combine, in fact, the advantages of neural networks with, in fact, sort of what we know about numerical analysis. So trying to actually solve or embed and enforce that differential equations hold within, in fact, the training of a neural network. How is this done? Well, essentially, it's done like training an interpolant on steroids. You train, in fact, a solution, or like you train a neural network, which becomes a mapping simply from your space of independent variables of your system of differential equations to your dependent variables. So you simply try to model, in fact, your solution as an interpolant. And how do you then actually enforce the differential equation? Well, that is done at the stage of training of the neural network. You simply define a loss function which takes into account the system of differential equations, the initial conditions, and if applicable, the boundary conditions. And I say this already a few times, it's kind of trained as an interpolant. So you essentially have to say, okay, where should, in fact, these conditions hold? So you simply have to sample your domain at finitely many collocation points. So you have, let's say, you solve a PDE in space and time. You cover your domain in space and time with finitely many collocation points. And in each of these collocation points, it's like your computational mesh, if you so wish. You enforce your condition that the system holds, the initial condition holds, and that the boundary condition holds. And then it becomes simply an optimization problem, or a training of a neural network, if you so wish. So you simply define, in fact, these conditions, sort of encode them as loss functions. Those are typically standard mean squared error losses, and then simply optimize the network to minimize these losses. And in other words, I mean, you should interpret sort of these physics-informed neural networks as a competing approach to solving differential equations. Because one of the advantages, if you ever work with neural networks, is that you have automatic differentiation available to you. So you do not have to discretize, in fact, your sort of differential equation anymore in terms of classical derivatives using sort of, say, finite differences. You can simply, in fact, compute the derivatives of your interpolant, your solution, using automatic differentiation. That makes, in fact, the whole procedure really nice and attractive. So that's like a still fairly high-level overview if you have never seen this, but it's a math talk. So let's take a look, in fact, at how this works in practice. So this is our setup here. So we have our system of differential equation, our initial value operator, our boundary value operator. And in fact, so we have to define sort of, I guess our goal is to solve this differential equation. In other words, we want to know, okay, what is u as a function of t and x. So we define a neural network which outputs u and inputs t and x, and then in fact simply try to enforce these conditions to hold. So how do we do this? Well, so okay, so there is a lot of material on these two slides, but just let me try to break it down. So this is still our differential equation, I guess, defined over our domain of definition, our initial value operator, our boundary value operator. But if we train a neural network, we can't in fact enforce this condition to hold everywhere in our domain. So we need to restrict ourselves to finitely many points. So in other words, we sample simply our domain. So our original domain is omega in sort of spatial dimension, and in fact this interval from 0 to t final in time direction. So we simply sample this domain at finitely many collocation points, which have this sort of little subscript delta here. And there is a total of n delta of these. And in fact, at these points, we want that the differential equation holds. So we simply, the differential equation should hold, it should equate to 0. Same for the initial and for the boundary operator. So in other words, we can simply define a mean squared error based on the left-hand side of our system of differential equations, right? Like if we exactly satisfy our differential equation at these collocation points, then this term would be identically 0, right? And same, in fact, for the initial value loss and the boundary value loss, which is defined, in fact, on a separate set of initial and boundary collocation points. Let me try to show this to you just to make this clear. So this would be taken from, in fact, the numerical solution of the Shallow-Water equation on the sphere. So we have a latitude, longitude coordinate system for simplicity here. So our domain is two-dimensional in space, and we have one time direction. So our total domain is three-dimensional in space and time. And in fact, these black dots correspond to the collocation points for our differential equation, meaning at those points I try to enforce my differential equation here. And in fact, at the blue points here, that's my initial condition at time t equal to 0. I try to enforce, in fact, my initial value loss. And the boundary value loss we ignore, and I explain this later on why we can ignore this. And then essentially, okay, so we define this, that then it becomes basically an optimization problem, right? Our neural network here, so we try to model our solution U, in fact, as a neural network which accepts our independent variables as input. So in fact, now it remains to find the parameters of this neural network. And then it becomes simply a training problem, right? So we enforce this, or we want to enforce this at our collocation points, and then simply have to find the optimal parameters of theta, and that we can do with standard deep learning frameworks. And so there is nothing then different anymore from training standard neural networks. And yeah, so by simultaneously minimizing this loss, so of course, one complication, if you know about like deep learning, if you know about optimization problems, it's actually, okay, so what we really want, we want that these loss terms individually as 0, but it's hard to do this. So in fact, we define like this combined loss here, sort of like an optimization method with constraints. And in fact, use this, in fact, as a proxy for, in fact, solving our problem. And this sometimes works and sometimes it doesn't work. And there is reasons for that. And maybe I'll have a little bit of time to talk about this. But yeah, essentially, like once you define the problem like this, you simply implement this in TensorFlow, PyTorch, and then it basically treats this as just finding the optimal parameters of your neural network. And I already mentioned, like one of the really main appeals here is that we can compute the derivatives essentially analytically using automatic differentiation. And that's really why this is so nice, in fact, on surfaces, because if you use numerical differentiation on surfaces, it becomes really challenging, right? Because you have to mesh, in fact, your surface, define like finite differences or other types of, like, say, radial basis function methods. You have to define the connectivity, you need to find nearest neighbors and so on to define your computational stencil. And all of this goes away, in fact, if you use automatic differentiation. So this method is just as easy to implement in Cartesian coordinates as it is, in fact, on sort of arbitrary surfaces. So, and then it's like really like a very simple idea. Okay, how can we do this then? Well, we just combine this with these existing embedding methods. So, and for the, I guess we use this radial basis function based method, this paper by Shankar here. And for simplicity, for the time being, we assume that the only derivatives of interest here come from the gradient operator, or sort of, so to speak, higher powers of the gradient operator. And we assume that sort of in the title, I guess, that our surface is orientable. So meaning we can define in each point the unit normal vector. And if we can do this, so then we can also define a projection operator, which in fact takes any sort of vector field in R3 and projects it on the tangent plane of the surface on our manifold. And then we can essentially simply define our surface gradient operator as basically matrix multiplying, in fact, our nabla with, in fact, our projection matrix here. And likewise, we can define Laplacian, B-Laplacian, and so on. So it's, I mean, it's using sort of, like I said, so we restrict ourselves here, like for this gradient and Laplacian operator, but lots of interesting equations, in fact, on surfaces are formulated in terms of these differential operators. So let's see how we can do this. So first example, shallow water on the sphere. So we first implemented this actually is simply in standard latitude longitude coordinates. So actually not even using this approach at all, because we thought, okay, why not use it in latitude longitude, right? So let's see, does the problem with the singularity poles really affect us here? Because we don't do numerical differentiation, right? Meaning if we don't have a collocation point precisely at the poles, like there should be no singularity, in fact, in our computation. So we tried this out and it actually does work to 90%, but it does fail, in fact, if there is a vector field which advects over the poles, because we can't define a vector field, of course, in latitude, longitude coordinates that goes over the pole. So let's walk you through this computation super quickly. So one of the things that neural networks are notoriously bad at is if in fact you have variables that range over vastly different ranges. And that's unfortunately the case here. So the u and v, the velocity components, it's like 10 to 100 meters per second, something like this. But the height field, in fact, goes to say 10 to the power of 4 meters. So in other words, in fact, the scaling isn't right for application to neural networks. It would be really hard to train a neural network, in fact, without rescaling the system of equations. But yeah, we can do this, of course. I mean, this is done all the time in fluid mechanics. So we simply introduce this characteristic length scales and time scales to get a non-dimensional version of the system. And this system we can basically implement sort of train a physics-informed neural network for. So we've done this. I think I spare you the details about like the architecture because it's fairly standard. It's a standard feed-forward neural network, and we use a hyperbolic tangent activation functions. That's maybe the only like really interesting thing here is, as in more modern deep learning, we use these rectified linear units. But of course, we want to differentiate our sort of neural network with respect to our input. So we use a activation function that is differentiable. And then the only other thing you have to be mindful is how you in fact define your computational nodes, these collocation points, because of course, if you use latitude, longitude, you get this clustering near the poles. But yeah, this is basically just a remapping, in fact, to account for the convergence of these meridians. And then you can almost sort of evenly distribute points on the surface of the sphere. And I think the only other thing here that is crucial is coming back. Let me just jump back here for a second. So this loss function that I showed you here, I mean, once again, that's not really what we want, right? We really want, in fact, the like that our differential equation holds that this term is equal to 0, this term is equal to 0, and this term is equal to 0. And of course, yeah, I mean, if this composite here would be 0, then this is satisfied. But the problem is, okay, if this is not 0, and it never will be 0, of course, because we use a numerical optimization. So then the question is, okay, to what degree actually are my initial conditions satisfied, my boundary conditions satisfied, and my PDE satisfied. And it turns out that these so-called multi-objective optimization problems are relatively hard. It's actually a multitask learning problem where we try to solve actually multiple tasks at the same time. And the problem is, in fact, if these tasks don't align with each other. So what do I mean by this? We use first order gradient descent. And if, in fact, the gradient associated with, in fact, the loss function, the PDE loss function, doesn't align, in fact, with the gradient direction of the loss of the initial value function, then the optimization algorithm would stall. And it turns out that there has been some work done recently on this, and the authors have coined the term the tragic triad here, that indeed these multitask learning problems do fail due to, in fact, gradients not pointing the same direction, where in fact one gradient being vastly larger than the other gradient, and high curvature being another culprit, in fact, for optimization issues. So in other words, it's not quite as simple to sort of simply sum up these loss terms and hope that everything works out. But there is like heuristic approaches to overcome this. I mean, really, it's like a so-called Pareto optimization problem, but like a more sort of simpler heuristic strategy that we used here is basically just taking from this work on this multitask learning problem to simply project conflicting gradients. So if gradients point in opposite directions, then we simply project one gradient, in fact, in the direction of the other gradient before we carry out one sort of gradient descent step. And that basically allows us to avoid being stalled in suboptimal minima. So it's a relatively simple strategy to implement, and it allows us to get numerical solutions that are sufficiently accurate. And sort of the last, I guess, thing that we noticed here, like one really challenging thing of, I guess, this interpolation, I guess, interpretation of this problem is that sort of the longer times you want to solve your problem, the more collocation points you really need to distribute over your domain, right? Because you really train, in fact, the solution as essentially an analytical solution or an analytical function, in fact, over your entire domain in space and time. So the longer you integrate, the more collocation points you have to use, and the harder it becomes to, in fact, train your neural network. And what I found, like implementing this in practice, is that once you go to actually timescales of interest in meteorology, you always essentially always decay your solution to a trivial solution. So the neural network doesn't learn, in fact, if you try to train it over the entire domain at once. So, and then of course, like the simplest idea you could come up with is where you just split your domain into non-overlapping subdomains and train a separate neural network on each of these subdomains. So like once you're done with the first subdomain, you simply use, in fact, the trained neural network, in fact, at the final solution that becomes, in fact, the enforcing initial condition for the next subdomain. So you essentially sequentially train, in fact, a chain of neural networks. So that's not parallel, of course, and that's something that we work on at the moment to try to parallelize this using some sort of standard parallel in time ideas. So yeah, basically it's like I guess picture is better than 1,000 words. So if this was our entire domain, okay, now we split this and train one neural network here. Once we are done, in fact, we just use this neural network to evaluate our new initial condition and continue. And that works then sufficiently well. And I don't think I want to talk too much about this here and in the interest of time. But essentially, it is really nice because if you sort of train your neural network for, say, like a final time t final, and you say, okay, I want to train a little bit longer, you don't have to start training from scratch anymore. So you simply add, in fact, more and more neural networks the longer you want to get your solution for. So let's test this out. So first example, cosine Bell advection. So this is simply solving a linear advection equation on the sphere. And essentially, so you begin with like a blob here, and this blob should be advected, in fact, over the sphere. It should be advected, in fact, depending on how you align your advecting velocity field in various directions. And this is the particular case where we advect over the sphere, over the pole. And in fact, the analytical solution has been designed in such a way that after 12 days, you should arrive back at the starting point. So you can combine, in fact, or sort of compare the initial solution to your final solution and get sort of a measure of the error going here. So in the sort of accuracy, something like of the order of 5% here in this particular, I guess, configuration. So you can get higher accuracy, of course, if you have more collocation points, but then you need also longer training times. And at the time of doing this, I simply didn't have the GPU resources to get higher accuracy. But it's a technical problem. It's not necessarily a conceptual problem. And this works because it's linear advection. So this works, in fact, essentially in latitude, longitude coordinates. You can still, in fact, advect this sort of cosine bell over the poles without problem. The problem arises, in fact, if you try out this test case, which is a global steady state nonlinear geostrophic flow. It's a really boring test case. It's essentially just a steady state flow, which you can align in various, in fact, angles, in fact, to the sort of to the poles, so to speak. And the problem is if you choose an angle which is different from 0, so you get the velocity field over the poles, and then in fact this latitude longitude coordinate system breaks down, unfortunately. And this is then when we had to use this embedding approach, where we essentially simply embed this in 3-dimensional space and simply solve our linear advection equation. So it's simply the velocity in times the gradient of h. So we simply, in fact, replace the gradient with the projected gradient, and then you're able to solve, in fact, this test case for arbitrary, in fact, velocity fields. So you can do some convergence here, and this is sort of just studying the impact of the neural network architecture and the number of collocation points, in fact, on the accuracy of the method, because we have an analytical solution. That's the only test case on the sphere where we have an analytical solution for the full Scheller-Water equations, that is. And yeah, it shows, okay, so the more collocation points you have, the more accurate the method becomes. And sort of the deeper the neural network becomes, sort of the more accurate it becomes as well. It's quite slow convergence, but it does improve in accuracy. Yeah, then I can show you some sort of little video clips. So this is the zonal flow over an isolated mountain. So there is a little mountain located here. You begin with this zonal flow that I guess showed you before. And then basically it starts to form like this standing wave after the mountain. So you see the emergence of these gravity waves. So that's one of the test cases we do all the time on the sphere for new numerical methods for Scheller-Water. So you see this quite frequently in the lee of the Rocky Mountains, for example. Rocky Mountains perfectly aligned in a way, right, to the east-west flow. And you see this sort of wave pattern quite frequently to the east of the Rocky Mountains. We compared this to another numerical algorithm, and once again, we get sort of an accuracy of like 5%, sort of an error, relative error of 5%, which is rather impressive given the computational sort of computational mesh that we use, because in comparing this to a standard numerical method, we use by several orders of magnitude fewer collocation points, as standard numerical methods would use mesh points. So really quite accurate result for very little computational effort. And sort of next case is just the Rossby wave, and that works as well. So it's another of these test cases. So let's move on now, like away from the sphere. I mean, it's a talk on solving equations on general surfaces. So let's solve the linear heat equation, now already written in terms of the surface Laplacian. And I want to solve this on two surfaces, a bumpy sphere, so a sphere where we simply add some bumps, and one of these sort of parametric surfaces that's studied in differential geometry, so-called Boy's surface. And yeah, so then of course the first question that I don't want to talk too much about this, because that's sort of, as I said in the beginning, a separate topic. Once you settled on a surface that you're interested in, like how do you, in a way, mesh this surface? Like how do you define, in fact, these collocation points? That's why I chose first of all the bumpy sphere, because once you have collocation points on the sphere, you just have to create some bumpiness in the radius, so that's no problem. And for Boy's surface, that's written in Python. I simply used some of these Python meshing libraries, PyVista here in particular. So then we simply, in fact, use this sort of built-in representation of Boy's surface to get these collocation points in space. And then we simply add a time dimension, just as we have done for the spherical case. This is like a numerical result, like heat diffusion. So I begin, in fact, with like 2 heat bumps, in fact, on the poles. And as you, in fact, integrate this with time, you get, I mean, as expected for a heat equation, sort of this heat diffusion over your domain. And this is, if you've never seen this Boy's surface, this is a Boy's surface. And once again, starting with like some initial heat distribution. And as you integrate in time, you get sort of nice heat diffusion over the surface. And as sort of a last, I guess that's a work in progress in a way, sort of like this problem of animal coating, like how do you get patterns on animals sort of simulated. So there is various models that people use. One of them is the so-called brusellator model. It's like a reaction-diffusion equation in 2 components. And then there is a set of parameters that people use, and that's sort of what we are working with here. And obviously, okay, if you want to do something on surfaces, we have to do this on the Stanford bunny as sort of a classical case. So then we can simply use, in fact, the geometry of the Stanford bunny from this Stanford 3D repository. And then simply okay, implement our projected gradient method for our physics-informed neural networks. And this would be sort of like a tentative result to begin with, like an essentially arbitrary initial condition. So like if you so wish, like so color pigments in a way, and in the end you get like a sort of a kind of a fur of a bunny which has some sort of coating in a way. And I mean, I guess once again, okay, maybe just to wrap this up, just to say a few words. Like one of the, I mean, I have to say it's nice because I'm working on this. One thing which I think is nice about this method is that really, like once I'd written, in fact, this for the solving the equation on the sphere, it took me a day essentially to solve it on the bunny, because there is nothing, in fact, different like for this method on the bunny compared to the sphere. Because, okay, simply I have to know, okay, what points lie, okay, what points define, in fact, this bunny. And then, okay, I have to get the normal directions. But yeah, for this, in fact, we can use meshing tools. And once I have this, the entire method doesn't change anymore, right? The sort of physics-informed neural networks approach isn't dependent on sort of like whether that's done in Cartesian coordinates, spherical coordinates, or in this case, sort of general 3D embedding coordinates. So that was like really, really nice and relatively easy to implement. And I think that the main thing why we want to work on this is to really illustrate that these sort of neural network-based methods are entirely meshless. I mean, that's not, I mean, of course, that's obvious in terms of the definition of this method, but it's not something that is stressed quite as much as it should be, I think. Because it is meshless, it yeah, by definition, it doesn't use a mesh. So meaning the problems of grid imprinting go away, right? That I mentioned before, that are plaguing, in fact, lots and lots of, I guess, mesh-based methods on the sphere, where you always see some sort of grid imprinting artifacts. And that doesn't happen here. And like one thing that we also found, it doesn't even matter too much how regular your collocation points are distributed. I mean, here, of course, we just chose, in fact, these given collocation points from essentially this scanning repository. And they are, of course, fairly evenly spaced. But we experiment around a little bit for the bumpy sphere case. So it doesn't really matter if the collocation points aren't absolutely evenly spaced. Of course, it does degrade at some point the accuracy of the method, but unless you go really crazy with your uneven collocation spacing, you should be really good to go. So that's once again driving home this, I guess, meshless part of this algorithm. One thing that we didn't have too much occasion to do is the parallelization aspect. I mentioned, I mean, I only have so much, well, I only did have so much GPU power available. That has since changed. So I'm kind of looking forward to trying this out. So for, I guess, larger scale problems or less toy problems in a way. In which case, of course, you have to think about parallelization of your training, maybe train across multiple GPUs, but it becomes a standard technical problem for deep learning then, right? So we can use everything that we know on training really large neural networks for like large data sets. We can apply here then as well. But yeah, okay, it's like this method, of course, isn't perfect. So there is like no free lunch in, I guess, numerical analysis. One of the things that I find really challenging with this method is to enforce hard constraints. So say coming back to weather prediction. So there are certain I guess, constraints you just want to see enforced, like mass conservation. The atmosphere shouldn't lose mass over the course of a simulation. But it's really hard, in fact, to enforce this as a hard constraint because it's a global constraint in a way, right? And if I go back super quickly to my loss function, so this loss function, in fact, once I train this, in fact, I train this mini batch wise, right? I, in fact, okay, sample my loss at finitely many collocation points, and then do a gradient step. So we just use the standard mini batch gradient descent as is used in deep learning. But in fact, if you want to say preserve mass globally, right? So then it's not quite clear to me how you can do this sort of using a mini batch gradient descent, because you really have to, in fact, take into account all of the mesh points or all of the collocation points at once. So that's not trivial. There is ways, in fact, that people try to solve this using some sort of domain decomposition ideas and apply essentially Gauss theorem to control the fluxes in and out. And then, yeah, you can do this, in fact, on subsets of your points, of course. And that does improve conservation, but it's not quite trivial if you want to have conservation up to machine precision. And lots of numerical weather prediction, or I shouldn't say weather prediction models, but lots of research models, in fact, on solving equations on the sphere try to get stuff like mass preserved up to machine precision. So that's challenging, and I guess still more research needed. And that's the end of it. So if you're interested in this kind of work, there is a preprint on the work on the Scheele-Watte equation available on arXiv. The stuff on surfaces is under preparation, so it still may take a little bit to finish this up. If you're interested in reading one of the first references on people using neural networks to solve differential equations, so check out this reference here. If you want to solve differential equations on surfaces but don't want to use a neural network, so these two references is quite nice. The closest point method, the RBF method. If weather prediction is your thing and you want to really see how hard it is to come up with grids, that's this reference here. And otherwise, I guess for a standard, I guess a way of solving equations on the sphere for weather prediction, this would be, I guess, this reference. And that's it from my side. Thank you very much for your attention. And once again, thanks for having me here.
Thank you, Alex.
Thank you, Alex, very much for the great talk. So we have plenty of time for questions. So feel free to type in the chat, or maybe raise your hand, or just unmute yourself if you have any questions.
Yeah, maybe I'll start it off. Of course, I'm an optimizer, so I'm going to ask about the multi-objective optimization. That was probably just a side note, but that's how it goes, you know. if you didn't want to talk about it, you shouldn't have.
Oh, that's fair. That's totally fair.
So what do the problems look like in your case? I mean, multi-objective optimization is a big field in a sense.
Yes. Yeah, so I think the problem that we found, and I'm not an optimization guy, so maybe you can help me out here. So so basically these are my loss functions, right? So I want to solve in fact the differential equation. So the differential equation has to hold. So in fact this loss should be 0 over my collocation points.
Yeah.
Initial conditions should hold, and yeah, okay, so I sort of ignored a little bit the boundary conditions. And so then the problem is, of course, okay, if this should hold and this should hold, and you essentially just add these components here together. So like, what's your guarantee, in fact, that the sort of the direction of like steepest descent, in fact, from this loss component points in the same direction, in fact, as in fact this component here. And if they point in essentially opposite directions, right? So then your optimization method would really stall.
Yeah.
And that's something that's unfortunately fairly common in deep learning, right? So that you have more than one optimization problem. And like one thing that I don't, like I said, I don't understand this like theoretically. One thing that I noticed when this crops up is if my domain is really large. So if I have like a very sort of thin domain in terms of time, so meaning most of my collocation points are fairly close to my collocation points, which I need in fact for my initial condition, then there is no problem, right? And it kind of makes sense, right? Because the equation is continuous. So some of these initial conditions and the, I guess, PDE, right? So in like, I guess like a hand waving speaking, I would believe, in fact, that they belong together so closely that these gradients should not diverge in different directions. But for, in fact, like once I'm like far away from my initial condition, right, and I'm sort of in a different part of my loss surface, so to speak, for my PDE loss, like who guarantees me, in fact, that I, like if I want to improve my PDE loss, that I still improve my initial value loss? And then essentially, like how this showed up for us in our simulations was that at some point the solution just decays to something really trivial, like typically to some sort of steady state. Like so this Rossby wave solution just essentially decays, like this Rossby wave solution decays essentially to this solution.
Yeah.
And so there is different ways, and I mean, you know this then better than me, I guess. Like if you want to solve this as a multitask learning problem, then you have to find this Pareto optimality. And there is different ways also in machine learning how people try to tackle this. But like in terms of like an algorithmically simple way of implementing this, I found sort of this sort of heuristic method the simplest.
Okay. Yeah, thanks.
I mean, if you have like a better idea, like say if I ask you, so
the thing is that what can you go back to that slide that you started with? I mean, what you're looking at there is really, I mean, it seems more like the first L sub delta is really the objective function you want to minimize, and the others, it looks more like a Lagrangian function that, or like a penalization function there. I mean, it's not you don't really want to minimize. I mean, you want to satisfy the conditions for Li and Lb. It's not really. But then again, I'm not a multi-objective guy. It doesn't have even like this multi-objective flavor. It's really more a constrained optimization problem. What you're doing is you're just writing it out as a penalized
that's exactly
problem. But I mean, it's so non-convex that you can't guarantee anything probably, even and you don't know how to tune gamma I and gamma p.
Yes, exactly. That's another problem. I mean, people have done like there is some extensive literature on that to try to, in fact, okay, what's the right scale, in fact, for say in your language of these Lagrangian multipliers here. And like people came up that you have to adjust them dynamically, right, to make sure, in fact, that sort of these loss contributions are sort of comparable in size, right? Because if one of these loss contributions is significantly larger than the other, then this will in fact dominate your gradient step. So it becomes quite non-trivial then to do this, to constantly adapt this. And there is different ways people try to solve this, to make, in fact, this also like a side constraint of your optimization, like what these gammas should be. Like it would be, I mean, it would be great to find, okay, what's the canonical way of doing this, right? To make sure that all of this holds.
I mean, but that might as well be complete garbage. But like augmented Lagrangian is something that people have been really working on recently, and that seems to be extremely stable for solving non-convex problems. Could
right.
to nothing, but that's a direction where you could, in which you could look.
Yeah, I'll check that out, because really, I think, I mean, great that was the first question. I mean, I think when I said in the end, I guess that sort of this level of accuracy that I get here is like always at around like 1%, 5%. It seems like even if I have like more and more collocation points, there is some sort of saturation happening at some point. And I think the reason is because my optimizer doesn't get sort of any close. And that may be related to that this is done with a first order gradient descent. And of course, yeah, it's a first order method. There is only so much, in fact, convergence you can get in finite amount of times. But yeah, I mean, it's challenging, and really, like, people started to analyze this more theoretically, right? So to try to, okay, where is the errors coming from? And we understand quite well the generalization errors of neural networks these days, of course. But we have a really hard time, in fact, understanding the optimization error, right? Because it's like such a generic thing, right? Like you said, it's like a non-convex, in fact, lost surface. And the question is, okay, so how can you guarantee that you get, in fact, to a good minimum?
Yeah. I mean, again, so the just straight up penalization as a numerical method is almost daring in a sense. I mean, that's basically the first kinds of methods that were like invented for constrained stuff, but they're numerically not excessively stable. And I don't know, in your large scale setting, I think I would try something like augmented Lagrangian for sure.
Right.
I'm not an expert in the numerical intricacies there, but all I can say is that stuff has been used a lot recently and studied from a theoretical and practical perspective.
Right.
All kinds of settings.
Yeah, there was another comment in the chat.
Yeah,
I'll have to look into
we have
this.
a question in the chat. Yeah, from Olivier Lafitte. I don't know if Olivier, you want to ask that in person or?
Yes, it was just a comment, but you already answered to that on the penalization method for constraints, in fact, because there are good theorems for Uzawa's method when gamma is large. But I think it's exactly the case where you will have problems of conflicting gradients.
Yes.
So just to check that. Thank you.
Okay, perfect. No, thank you. I appreciate like these pointers, because like I'm not an optimization guy, right? Like for me, I just have to piece this together. So that's great. So that's really helpful, these two comments to look into this, and maybe that helps to improve some of the overall accuracy that we can get with this method.
Right. So I had a question about, actually, in the conclusions you were mentioning in the bunny example.
Yes.
So that you needed the normal vector, and for that you used some meshing method.
Yes.
But then you said this is a meshless method. So then I got confused. Like.
Right. Yeah. Right. Yes. I know what. Yeah. Yes. So okay. So what is true, in fact? Okay. So what do I mean by meshless method? Right. So a mesh for me, I mean, okay, it's maybe like a question of terminology, but if you study meshless methods, like meshless numerical methods, I guess the meshless nature always refers to the, I guess, fact that you don't have any connectivity between your nodes, right? So there is not that there is like some natural ordering in your node, so that there, like one node has neighboring nodes, right? That's sort of what's meant with meshless. That's why I try to call them collocation points, right? Instead of mesh points. But you're right, of course. I mean, we do need to define some sort of normal direction, right? And if we define some normal direction, then we need to have some sort of, I guess, idea of the neighboring points, right? To define like what is a good normal direction. And this is, I mean, there is then, that's the part that I wanted to, I guess, skim over. Then you have to look into, okay, how can you actually, if you're given a point cloud, how can you actually mesh this? And there is different, I guess, algorithms available for this. How you can basically, if you're given a collection of like nodes without any connectivity, right? Like how can you in fact reconstruct the surface? It's like a surface reconstruction problem. And there is some good algorithms out there, like this rolling ball method, where you just make sure, in fact, that there is like no gaps, in fact, in your points, and you essentially get this smooth, in fact, sort of almost like a hull to your points. And once you have this, you can get the normal vectors. And the good thing is, I guess here is that we simply, or I guess the sort of convenient thing is that this is implemented in Python, right? Like if I give Python essentially a point cloud, then I can use, in fact, these algorithms to reconstruct the mesh, the surface from, in fact, the point cloud. And once I have this, I can get the normal vectors. And from that point onwards, like then the numerical algorithm is meshless in the sense that it doesn't really matter if you have neighboring points, right? And you can illustrate this, like I said, if the collocation points aren't evenly distributed. I mean, it degrades your accuracy, of course. I mean, of course it does. But at least there is no, in fact, like conceptual thing that requires you to get like a super precise mesh. I don't know if that answers.
Yeah, yeah, thank you.
Awesome.
So I think there is another question in the chat from Leon Glass. Please go ahead if you want to ask the question in person. Otherwise, we'll read it for you.
Hey, for the Brusselator model, typically that's a model of oscillations. I'm not sure exactly what it is for the parameters you use. It can be an excitable medium also. Can you comment on what eventually happens in that model?
Yeah. I mean, I think there is if I'm not mistaken, the original Brusselator model was like a dynamical system, and then people extended this, in fact, to a PDE model. So it's what does happen is, in fact, depending on your parameters and depending, in fact, on in particular your diffusion coefficients here, you get sort of different like steady state solutions in the end, which sometimes called this Turing pattern. Like it's basically like distinct pattern, like stripes or like points, basically like say a leopard or a zebra. So like how do you get, in fact, the stripes on a zebra? So you have to find, in fact, the right parameter combination to end up, in fact, with this as an asymptote.
So the parameters you have evolve to a steady state rather than oscillations.
It depends. It depends on the parameters that you do choose. So there is oscillating regimes as well. So this one here in particular, if you integrate this long enough, should actually lead to stripes or dots on the bunny surface. And that goes back to what I said before. We have to run this really long. And that's why it's work in progress. I haven't been able to run this long enough to actually get the stripes and the dots. But yeah, so in short, to answer your question, as far as my understanding is from this model, it does depend quite strongly, in fact, on your parameter combination, whether you end up in a steady state or in this sort of oscillatory regime.
Right, but the reason it's called a Brusselator is it's a combination of Brussels and oscillator. but of course it could have. But for your parameters, is there a stable steady state in the ODE?
I'd have to check. I've taken this. In fact, that's one of the examples I think that was tried out in this paper. So I'd have to go back and see. So why they chose this particular configuration. I think, as far as I recall, they just simulated this long enough, in fact, to get these stripes, in fact, on the animal coat. But I'm not sure if they comment on what would happen if you were to run this even longer. So that's a great question, in fact. So like what would happen asymptotically here? So I don't know the answer to this one.
Okay, thanks a lot.
Thank you.
All right, so I think it's 5:05. Maybe we can end the official discussion here. Thank you again to Alex, the speaker, and to all the participants to having a great discussion.